Time again for some quick integration practice. In this case, we're solving the integral of x divided by x to the power of 4 plus 4x squared plus 8. And before we dive in, we need to convince ourselves that we're not dealing with a standard integral. And in this case, the integral that comes closest is the integral of 1 divided by 1 plus x squared dx, which is of course the tangent inverse of x. However, we see that we're quite far off from this one, so no luck in this regard. The first step then is to see what is the most defining part of our integral, or the most complex looking thing. In this case, it's the fourth order polynomial in the denominator, and we obviously want to get rid of it. Now we note here that this is not an arbitrary fourth order polynomial. It only has powers that are even, x to the power of 4 and x to the power of 2, no x cubed or simply x. Therefore, a viable option here is to use substitution. We can, for instance, choose our substitution parameter, u, to be equal to x squared. This of course means that du will be equal to 2 times x dx. And we see that by doing this substitution, we not only get rid of this fourth order polynomial in the denominator, but we also address this x in the enumerator, because we have x dx, which is exactly what we have here, only without a 2 in front of it. So we can now rewrite our integral performing our substitution. So we get the following integral. In the enumerator, we replace x dx simply by du divided by 2. This means that in the enumerator, we get 1/2 du. And in the denominator, we simply replace x squared by u. So x to the power of 4 becomes u squared, plus 4 times x squared simply becomes 4 times u plus 8. And we can rewrite this even further to get 1/2 times the integral of 1 divided by u squared plus 4u plus 8 du. And now we have reduced our integral, which had a fourth order equation in the denominator and an x in the enumerator, by an integral with only a second order polynomial in the denominator. And this form is actually quite common, and we want to rewrite the fraction inside of the integral as 1 over some variable squared plus some constant squared, because then we do get a standard integral, some variation on the inverse tangent. And to rewrite this fraction, we are going to use the method of completing the square, which basically uses the fact that a plus b squared is equal to a squared plus 2 times a times b plus b squared. Now, if we compare the second order equation in our original denominator with this form right here, we will try to identify it. We have a u squared, which will take the place of the a squared. So we have u squared here. This means that a is equal to u. Then we add to this our second term, which is 4u. So this will become 4 times u. And then we are left to figure out what the b squared will be. Now we know that this mixing term is 2 times a times b. So we should be able to get our b from this 4 times u. We know that a is equal to u, and we know that we have this 2 in front of it. So this is actually 2 times u times whatever is left in order to make this 4u. Now, in this case, this is of course simply 2, because if we multiply 2 times a, which is u, times 2, we indeed get 4 times u. Therefore, we know that b is equal to 2, and b squared will then be equal to 4. Now, doing this in reverse, we then see that we get u plus 2 squared. And so we've rewritten u squared plus 4u as u plus 4 squared. However, it's not exactly the same. We have this plus 4 here, which is not present in this u squared plus 4 times u. Therefore, in our original fraction, we need to add and subtract 4. And this is how it goes. So we know that our integral will be 1/2 times the integral of 1 over u squared plus 4u, which is what we actually have. Then we add 4 to make this term right here, but we need to subtract 4, of course, because we cannot simply add 4 and do nothing. And we have, of course, this plus 8 du. And now we see that if we have u squared plus 4 times u plus 4, which is exactly what we have here, we can replace it by u plus 2 squared, which is what we'll do. So we get 1/2 multiplied by the integral of 1 over u plus 2 squared. And then we're left with minus 4 plus 8, which is of course plus 4. Now this plus 4 can itself be written as 2 squared. So we get plus 2 squared. And we don't forget our du. Now we see that the fraction that we've obtained here is exactly the form that we wanted. 1 over something squared plus a constant squared. So at this point we are almost done, because we can rewrite it as 1 over 2 times the integral of 1 over u plus 2 squared plus 2 squared d of u plus 2, because we can always add or subtract a constant number inside of this d. Therefore, this looks a lot like the integral of 1 over x squared plus a squared with a constant, dx. And we know that the solution to this integral is 1 over a times the inverse tangent of x over a. And knowing this, we can simply fill this in and find our solution. So we get that this is simply equal to 1/2 multiplied by 1 over a, and a in this case is this 2, so 1 over 2 multiplied by the inverse tangent, so tangent to the power of minus 1, of the following: x, which in this case is u plus 2, so we get u plus 2, divided by a, and a in this case is 2. And this is our solution, but still as a function of u. And as a reminder, our integral was as a function of x, but we use the substitution that u is equal to x squared. So we simply have to replace u with x squared and we are done. So the solution to this integral will be 1 over 4 multiplied by the tangent inverse of x squared plus 2 divided by 2, or written differently, 1 over 4 times the inverse tangent of x squared divided by 2 plus 1. And this is actually a very neat example of how we can use substitution in combination with completing the square to solve a pretty daunting looking integral.